All right, so the handwriting is going to be awful today. I apologize. So let's start with a summary. So we had looked at the Hamiltonian. Oops. Which was defined to be the sum over I 1 to n of pi qi dot minus the Lagrangian. And then the equations of motion were given by the canonical equations. And that was that qi dot was di h by di pi, and pi dot was minus di h by di qi. And we also introduced the Poisson bracket of two functions. And that was defined to be the sum from I equals 1 to n, the number of degrees of freedom, of di u by di qi times di v by di pi minus the other way around, di u by di pi times di v by di qi. Where u and v are functions of the qi, pi, and potentially t. We also saw that the time dependence of any function, so given some function f of the qi, pi's, and potentially t, we found that df by dt, so the how f depends on time was simply given by taking the Poisson bracket of the function f with the Hamiltonian. And in principle, if f depends explicitly on t, there's a di f by di t in there. And so this is a very important observation, that the Poisson bracket of something with the Hamiltonian tells us how something depends on time. And we saw that that, in effect, was related to the symmetries of the Hamiltonian with respect to time. And then more generally, we looked at transformations and symmetries again, but now using the formalism of the Poisson brackets. So we wrote for a generating function G. So G generates a transformation of coordinates that we could write something like this, that the Qi primed is given by Qi plus the Poisson bracket of Qi with G. So G is some function, right? In principle of the Qi, Pi, and T. So given that function, one can calculate a transformation by taking the Poisson bracket of Qi with G, and then writing these infinitesimal transformations. Pi primed then goes to Pi plus the Poisson bracket of Pi with G. And so that's what we call G, the generating function of the transformation, because we can define, we're free to do so, a transformation that looks like this. And then the more remarkable thing is, we found that if the Poisson bracket of H and G equals 0, that means H is invariant to the transformation. So for H to be invariant to the transformation, I mean that H prime equals H. Then we found that G is conserved. And so of course that also means that the Poisson bracket of G with H is equal to 0. Okay, so any questions about that material? Okay. So today we go into a new chapter, which is chapter 8 in the notes. And it's called Canonical Transformations. So we've already seen that some choices of coordinates are better than others because they lead to some coordinates being cyclic, and then you can immediately find what we call constants of motion. In particular, for a cyclic coordinate, the conjugate momentum is conserved, and so a constant of the motion. In the Lagrangian formalism, it's not necessarily trivial to find a new system of coordinates that will lead to these simplifications, because you also have to figure out the time derivative of those coordinates, because the Lagrangian depends both on the Qi and the Qi dot. In the Hamiltonian formalism, we get rid of the Qi dots and we use the momenta, the Pi, instead, and we sort of promote these to independent coordinates from the Qi. And so we have a lot more liberty in testing different types of transformations. So the idea of this field of study of canonical transformations is to try and figure out a formalism for figuring out the best possible coordinates to use and potentially make all the coordinates cyclic. At the expense, of course, that now solving the equations of motion is trivial, but finding the transformation that makes all the coordinates cyclic is perhaps more difficult than if you do it the other way. That has a sort of a mathematical beauty to it and highlights the equivalence of the coordinate and the conjugate momenta as truly independent coordinates. So the idea of these canonical transformations, very generally, is so a canonical transformation of the coordinates and momenta we write it like this. We write that the PI will go to the capital PI, so that's the transform coordinates. The QI will go to capital QIs, so that's some transformation. And then the Hamiltonian, which we would normally write as a function of the little QIs, the little PIs, and T, we write as K of the big QIs, the big PIs, and T. Sometimes people will call K the Camiltonian, but it's not really. Chapter 8 is not posted. Well, I'm surprised. I apologize. Let me check. Yeah, chapter 8 is posted online. But maybe you can't see it. Oh yeah, I forgot to unhide the week. Okay. So now you can see chapter 8. I'm sorry it was posted but hidden. Thanks for pointing that out. Okay, so the Camiltonian, calling it the Camiltonian is not particularly useful. So it's still the Hamiltonian, it's just expressed in terms of the capital Q's and capital P's. So the transformation is canonical. Transformation is canonical. That spells canonical. If the canonical equations are preserved, that is, if it's still true that Qi dot is equal to di K by di capital PI, and P capital PI dot is equal to minus di K by di capital QI. So transformation is canonical if in the transformed Hamiltonian in coordinates, the canonical equations are given by the same math. Okay? So point transformations are canonical. So we've already encountered point transformations. Point transformations are transforms of the type Qi is expressed as a function of only the capital Qi's and t. So we've already seen and demonstrated that we can choose, say when we're doing Lagrangian mechanics, whatever choice of generalized coordinates that we want. So we're just changing the x's and the y's. We're not changing the momenta. And so we've already seen that the description of physics, the Lagrangian, the Hamiltonian, is compatible with any point transformation of the coordinates. And that means that the canonical equations will naturally be preserved. Okay? So let's look at general transformations. So general transformation, we're going to write as Qi is given as a function of the big Qi's, capital Pi's, and the t. So the difference with a point transformation is that the transformed coordinates depend on both the transformed coordinates and the transformed momenta. Right, and so that the Pi we can write as a function of the same thing, capital Qi's, capital Pi's, and t. And of course, we require that these are invertible. By invertible, I mean that you can write the Qi, as the capital Qi as a function of, well, in this case, it would be the little Qi, capital Pi, and t. So these are functions that you can invert. So you can go from one coordinate system to the other back and forth. Okay, that's the assumption. So that's just a general transformation, right? So we want to know what's the condition for this transformation to be canonical. That is, what's the condition for the Hamiltonian when evaluated as a function of the capital Q's and capital P's gives the canonical equations, that is that the time derivative of the capital Q is dk by dp, and the time derivative of P is minus dk by dq. Okay? So the equations of motion will be unchanged if the action is unchanged. Right, remember the action is the integral, the definite integral of the Lagrangian. That's a dt there. So the Lagrangian, remember, is given by the sum y equals 1 to n of qi dot pi minus h. It's the Legendre transform of the Hamiltonian. So what this means is the equations of motion will be unchanged if the action is invariant, or the equations of motion are unchanged if the Lagrangian changes at most by a total time derivative. Remember, you can add a total time derivative to the Lagrangian because the action is the integral of that. You're effectively just adding a constant to the action, and that doesn't change the equations of motion. Okay? So if we write the Lagrangian in our untransformed coordinates, it's just what we have up here, right? So we have the sum of I equals 1 to n of qi dot pi minus h. For the action to be unchanged, then that's got to be equal to the Lagrangian in the transform coordinates. So the Lagrangian in the transform coordinates is the sum from I equals 1 to n of the capital Qi dot times the capital Pi minus the Hamiltonian in the transform coordinate, which we called K. All right, so that's like the left-hand side is like L, and the right-hand side is like L prime. But that's not the most general case, right? The most general case is that L can actually change by up to some total time derivative. So we can add here the total time derivative on the right-hand side, d by dt, of some function f. And so the function f can depend on the big Q's, the little q's, the big P's, or the little P's. And it turns out that it has to depend, and we'll see different cases later, it has to mix the new and the old coordinates. So let's choose the case of it mixes the qi, the little qi, with the capital Qi's. And that can depend on t. So this function here must mix the new and old coordinates. Okay, so that's what we require. So we're going to find out the conditions for the transformation to be canonical by requiring that the Lagrangian is unchanged. So we can impose that the transformation is canonical, and that, so we'll find out what the consequences are. So for the transformation to be canonical, that means that capital Qi dot is equal to di k by di capital Pi, and that capital Pi dot is equal to minus di k by di capital Qi. So impose that. So consider the total time derivative of f. So I guess I'll write out explicitly that f depends on the little qi, the capital Qi, and t. So it's we want the total time derivative of a function that depends on the various things. So we use the chain rule. We can write that as the sum from I equals 1 to n. Inside the sum we have di f by di little qi dot, plus di f by di capital Qi dot, plus outside of the sum di f by di t. So we're going to put that into the equation that we have above. So on the left-hand side, it's unchanged. So I have the sum from I equals 1 to n of little qi dot pi minus h. And on the right-hand side, I have the sum from I equals 1 to n of capital Qi dot capital Pi minus k, and then plus the thing that I just wrote above here, so the df by dt, so that's the sum from I equals 1 to n of di f by di qi dot, so those little qi's, plus di f by di capital Qi dot, plus outside of the sum di f by di t. Let me rearrange this, and I'm going to factor the terms that have little qi dots and capital Qi dots. So I'm going to move the di f by di qi dots with the little qi dots to the left-hand side of the equation. So I have, starting on the left, I have the sum of I equals 1 to n of little pi minus di f by di little qi dot minus h equals, and on the other side I'll do the same thing, factoring the capital Qi dot, so I have the sum from I equals 1 to n of capital Pi plus di f by di capital Qi, so that's times capital Qi dot, and then I still have my minus k plus di f by di t. So I want to make this true, and I want the transformation from the little q's to the big q's, and the little p's to the big p's, to guarantee that this is true. Okay? So I can guarantee that this equation is true by imposing So I'm going to impose that this term is 0 and that this term is 0. So I'm going to impose that little pi is equal to di f by di little qi. I'm going to impose that capital Pi is equal to minus di f by di capital Qi. Remember, f is a function of the little qi, the capital Qi, and potentially t. So if those two terms are 0, the terms I underlined in red, then the transform Hamiltonian, so capital K, which I refuse to call the Hamiltonian, but capital K, which is a function of capital Qi, capital Pi, and t, then it's equal to the Hamiltonian h, which itself is a function of the Qi, the little Qi's, the little Pi's, and t, plus this di f by di t. So you can now think of this the other way around. So think of some function capital F of the little q's and the big Q's. We call that the generator of the transformation. The transformation is given by taking little pi equals di f by di little qi, and capital Pi is minus di f by di big Qi. So given some function f, you can generate these transformations, and then you can invert them. And then given that function f, you can now re-express the Hamiltonian k in terms of the big Q's and the big P's, plus this di f by di t. So that gives you now a prescription, given a generating function f, which is not trivial to figure out, but given that function, you now have a procedure that will give you a canonical transformation. Okay? So we call f the generator of the transformation and then for the transformation to be canonical, we have the conditions that I just wrote earlier. And those conditions were that little pi equals di f at qi, big pi is minus di f by di capital Qi, and the new Hamiltonian k is given by h plus di f by di t. And so this assumes that the coordinate transformations Qi can be written and can be inverted. So it's possible to choose to use either the capital Q's or the capital P's. And so if they're invertible, you can also write that capital QI is a function of little qi, little pi, and t. Okay, so given some transformation that you can write, if it satisfies the conditions that we have above, then that transformation is canonical. And that will guarantee that or the time derivative of capital Q is given by di k by di p. Let's go back to this. We actually only handled a specific case here. We handled the case where f depended on little q and big Q. So we in fact have 4 possible ways to mix the little variables with the big variables. Okay. So we have 4 possible types of transformations. Depending on what f depends on. So if f is a function of the little qi, the big qi, and t, we call these transformations of the first type. If the function f, well, let me write this like this, f equals f1. On the other hand, f equals some function f2 of the little qi's, the capital Pi's, and t, minus the sum from I equals 1 to n, capital Qi, Pi, and we call that a transformation of the second type. The third type is if f equals some function f3 of the little pi's, the capital Qi's, and t, plus the sum from y equals 1 to n of little pi qi, and that's the third type. And then the fourth type are the ones that have f equals a function f4, but now mixes the little pi with the big pi and t. And this one has 2 sums in it. It has the sum of little pi qi, and it has the sum of capital Qi, capital Pi. And we call that the fourth type. So these extra little sums that we put into the functions f, the end effect is that they cancel out the sum over q's and p's that you have when you impose those two forms of the Lagrangian or equivalence. So we just did that for the first case with f, and then we'll do later an example, I think, where I think it's one of the second kind, and you'll see that that term with the capital QI, capital PI ends up canceling a term that you need to cancel. The relations between these different generating functions, they kind of almost look like Legendre transforms. And so you might be tempted to think that for a given problem, you have a choice of which generating function to use. And that may be true, but it's not necessarily true. It's possible that although it would work for the second type, if you use a transformation of the third type, then you end up with, something that divides by 0 or something funny. So it's not necessarily true that you can just transform from one kind of transform to the other. And the other thing is, for a given problem, you might have a situation where the first coordinates transform, to get a very easy Hamiltonian in the end. It could be that the first coordinates transform as the first type and the second coordinates as the third type. So you could have maybe x and y that transform to x prime and y prime using a first type of transformation, and that maybe z and pz transform according to the third type or something like that. So you can have a very general systems. So all we've done so far is that we've shown that there is a formalism that allows us to rewrite the equations of motion in a different coordinate system. So there are transforms that can transform the q's and the p's and preserve the mathematical form of the canonical equations. And so it's already a very powerful statement to say that we can completely redefine what momentum and coordinate means, right? The capital Q's and capital P's could have crazy units that have absolutely nothing to do with coordinates and momenta. And we're just calling them Q's and P's to sort of keep the familiar notation, but they're not necessarily at all associated with coordinates or momenta. So the powerful statement here is that we can choose like some pretty odd-looking coordinates to describe a system mathematically that's equivalent to using coordinates that we feel good about, like x and y and px and py. So let's just do a couple examples of these transformations. There's a table that I wrote in the notes, table 8.1. So I'm not going to rewrite the table because writing with this tablet is a huge pain in the neck, but I'm going to box here these equations here. Those are the transformation equations, how to get little p and big P in this case, for transformation of the first type. So see table 8.1 in the notes for transformations of the second, third, and fourth type. Okay? So for example, in the second type, you need an equation that gives you the little pi and the capital QI. And so there's different signs here. So let's do an example. With a transformation of the first type. This is example 8.1 of the notes. So let's find the transformation equations. So capital QI in terms of little qi, little pi, and t, and capital Pi. So how do the big Q and big P depend on the initial variables? Given a generating function f that's given by the sum of capital QI and little qi. So f is a function of the little q's and the big q's. So f is of the first type. So if f is of the first type, then we can write that little pi is given by di f by di little qi. Right? That's the transformation we have in the box up here. So what that means, if I take di f by di qi, I select out the capital QI. But if I take, so think of f as being the sum maybe from j equals 1 to n of capital Qj and little qj, and I take di f by di qi, it's going to select the term from the sum where I is equal to j, or j is equal to I. And so little pi is big qi. And then big pi, which is given by minus di f by di capital qi, that's going to be equal to minus qi. So of course it's trivial to write out qi and capital pi, right? So I've already written out capital pi as a function of the little qi, the little pi, and the t is just equal to minus qi, and then qi as a function of the little qi, pi, and t is just equal to little pi. So what this transform does is that qi equals pi and capital Pi equals minus little qi. So this transformation, given by the generating function of the sum of the capital Q's and little q's, has the effect of swapping what we mean by momentum and coordinate and adding a negative to the coordinates. So it interchanges the momenta with the coordinates and put minus signs on the coordinates. And that's completely valid, right? We already described that in the Hamiltonian, you can describe it as the coordinates and the momenta are separate, so you can change what they're called, and the equations of motion are still the same. Well, that's basically what this just did. It changed the definition of which way the plus x plus y and plus z go, and then it swapped what we call momentum with what we call x position. So it highlights this really powerful statement that we can really describe the Hamiltonian in terms of whatever coordinates we want, and you can treat the coordinates and the momenta as mathematical entities that sort of lose their coordinate and momentum meaning. All right, let's do another one. let's do example 8.2. We'll just do the same thing, but now we'll use the function f. And the function f will be given by the sum over I of little qi, capital Pi. So it mixes the little q's with the capital P's, and that's the transformation of the second kind. So if we look in our table 8.1, we find that the pi's, so now that this gives us equations for the little pi's, those are equal to di f by di qi. And so di f by di qi is capital Pi. And the other one that we want is the capital Qi. And the capital QIs are given by di f by di pi, di f by di capital Pi. So that's a mistake in the notes. And so di f by di capital Pi is simply equal to Qi. So the little pi's go to big pi's, and the little QIs go to big QIs. And so of course that's just the identity transformation. So this particular generating function doesn't actually do anything. It transforms, it just labels the little p's capital P's and the little q's capital Q's. Alright. So let's do now a more useful example. This is the simple harmonic oscillator. Solved with the generating function capital F given by m omega over 2 q squared, so little q squared, cotangent of capital Q, where omega is just the angular frequency of the simple harmonic oscillator. Right, so the simple harmonic oscillator, the Lagrangian would be given by a half x dot squared plus a half k x squared. Right, that's the Lagrangian for a simple harmonic oscillator. So that's the problem that we want to solve with, or we want to see what happens when we use this generating function to transform the coordinates from the little q's to the big q's, little p's to big p's. All right. So if I use the form, if I instead of calling it x and px, I'll just call it q. So I'm just going to say that q is equal to x, right? So the Hamiltonian for a simple harmonic oscillator so this is a case where the Lagrangian doesn't expand on time, the velocity, the potential doesn't depend on velocity, and so the Hamiltonian is just equal to t plus v, right? And so the t term is p squared over 2m, and the v term is the same that we have here. It's k over 2 times q squared, right? So p is px, and q is x. So any questions about that? That I can write the Hamiltonian like this for the simple harmonic oscillator? The kinetic energy is momentum squared over 2m.
And
any questions about that?
Small p?
You can see it up here in the Hamiltonian. Yeah, go ahead. That's a small p, yeah. For now, we still have everything in terms of small p's and small q's. We're setting it up. And the goal is going to be to show that with this generating function, which introduces this capital Q, there's a new set of coordinates, capital Q and capital P, where the simple harmonic oscillator is trivial. Alright? Let me just, for future convenience, write this slightly differently. I'm going to factor out a 1 over 2m. So the Hamiltonian is 1 over 2m, and I have p squared plus m squared omega squared q squared. If you plug in this omega equals square root of, oops, that should be k over m, sorry. All right, if I plug in, so k is equal to omega squared over m, and if I plug that in here and I factor out a 2m, I can write the Hamiltonian this way. Okay. So f is of the first type. All right, it depends on little q and big Q. So if f is the first type, then the transformation equations are that little p is given by di f by di little q. So di f by di little q, q is just a q squared in there, right? So it's just going to pull down the 2. And so that's equal to m omega q. And then we still have cotangent of capital Q. The big P is minus di f by di big Q. And that's equal to m omega squared q squared over 2 sine squared of big Q. Right. So to do that, we had d by the capital Q of cotangent of Q equals 1 over sine squared Q. Okay? But what we want is we want Qi in terms of big Qi, big Pi, and T, and we want little pi to be expressed in terms of the capital Qi's, capital Pi's, and T. So we have to still invert these equations.
Yeah, how did you get the omega squared? Because F is just omega.
There is no square.
Okay.
That's how I got it.
No problem.
Too much ambition. Thanks for pointing that out. I think it's actually correct in the notes. No, it's correct in the notes. It was just a mistake of writing it down. Okay, so now we want to rewrite the Hamiltonian using the big Q's and the big P's, so we need to figure out how you write the little Q's and the little P's in terms of the big Q's and the big P's, right? So the Hamiltonian depends on little p squared and Q squared. And we want it to depend somehow on capital P and capital Q. So we already actually just wrote out here the second equation actually gives us Q in terms of capital P and capital Q, right? So I can write Q squared. I'm just rearranging the second equation that I have there. So Q squared is equal to 2 over m omega times P sine squared capital Q, right? Now I also want to write out what P squared is equal to. All right, so P squared is equal to this thing here. So P squared is going to be equal to m squared omega squared Q squared cotangent of Q, of capital Q. And so I already have an equation for the Q squared, for the little Q squared. Yeah. Same.
Don't we square the cotangent?
Yes, we do. And so that is, when you plug it in, it's 2m omega P cos squared of capital Q. Right? Remember that cotangent is cos over sine. So now we have Q on the left in terms of big P and big Q. And then we have little p on the left in terms of big P and big Q on the right. So we found the transformation equations. Now, K is equal to the Hamiltonian plus partial derivative of f with respect to time, but f doesn't depend on time. So K is just equal to the Hamiltonian, but expressed in the new coordinates, right? So the Hamiltonian was equal to 1 over 2m times p squared plus m squared omega squared q squared, right? And I just wrote out equations for q squared and p squared in terms of big P and big Q, right? So I'll just add those in here. That's 1 over 2m. So the little p squared is equal to 2m omega capital P cos squared of capital Q plus m squared omega squared times q squared, and q squared was equal to 2 over m omega P sine squared Q. So let's see. So let's look at the first term. The first term, the two m's cancel, and you're left with omega times p cos squared q, right? And then the second term, you have an m omega that's canceled because there's a denominator, there's a 2 over m omega, so that cancels an m and an omega from the m squared omega squared term. So that's with 2m omega. You divide that by 2m, so you're left with just omega. So the first term is equal to omega p cos squared q, and the second term is omega p sine squared q. All right, so we have k equals omega p times cos squared q plus omega p sine squared q. And factor out an omega p, and then I have cos squared q plus sine squared q. So that's equal to omega p. Yep.
Where did your m go?
The m's canceled, I believe. So in the first term, I have an m here, and then
it's
the
a
front.
2m.
Yeah.
Okay.
And then in the second term, I have an m squared here, one of them's canceled here, and one of them's canceled here.
I didn't have a 2m, I only had a 2. That was my confusion.
Yeah, the 2m is back at the front. That's why I wrote the Hamiltonian in this weird way here. I factored out the 2m. So I have to add an m into the q. Alright, so now, the new Hamiltonian in the transform coordinates is simply omega p. Well, that's exactly what we had promised in the beginning. Capital Q is cyclic. Oops. And so P is equal to a constant. Capital P is equal to a constant. And that constant is actually the energy over omega, because K, which is equal to the Hamiltonian, is also equal to E. So the trick here, of course, is to figure out the function f, which is not necessarily trivial, but given that function f, you now see that the Hamiltonian in the transform coordinates is trivial. It's just omega p. And so q is cyclic and the total momentum is constant. You find that out immediately. And then using the canonical equations, q dot is di k by di p. And so that's equal to omega, right? So that's also trivial to solve. And we can automatically find that q, capital Q is a function of t, is given by omega t plus some integration constants. Integration constant, I mean, it depends on the initial conditions. So we can transform this back into the original variables. So little q of t is given by the square root of 2 capital P over m omega times the sine of capital Q. That was this equation right here, right? We have q squared equals 2 over m omega p sine squared q. So if I take the square root of that equation, I have q equals the square root of 2m omega p, or 2p m omega sine q, right? So that's just that equation there. And now if I substitute in what we have for p and what we have for capital Q, I believe there's a mistake in the notes. So that's 2, and then P is equal to E over W, E over omega. I believe this should be M omega squared. In the notes, it's missing the squared. And then sine of capital Q is omega t plus beta. And so we find that this is like the x of t, right, for the simple harmonic oscillator. So we indeed find the correct normalization and that it's a sine. And so the simple harmonic oscillator oscillates. So this underscores how powerful these canonical transformations are, because we end up with this absolutely trivial Hamiltonian. But the part that was a little bit swept underneath the rug here is, how did I know that, you know, where does it start? How did I know that this particular form of f was going to simplify the problem? And so I know because I looked it up in a book. But the hard part, of course, is determining f. But given a clever choice of f, then equations are mostly trivial. That's pretty much the only one of the only examples that you can do analytically that works out easily. Any questions? Oops. Okay, if not, thanks everyone. Sorry for running a little bit over time for the technical issues in the beginning. I hope I'll get the tablet working again.
Dr. Martin?
Bye.
On question 2 of the homework, I saw your email.
Yeah.